Welcome to AI Paper Slop. Today we are looking at Zero, a scalable 3D interaction trace world model. And if you are building robot learning systems right now, you know your primary bottleneck is basically a lack of action-labeled data.
Right, it's the biggest hurdle in the field.
Yeah, so instead of training world models to predict like wasteful dense pixels or forcing them to predict embodiment-specific actions, Zero predicts smooth 3D interaction traces.
Exactly.
It maps out the trajectory paths of objects and, contact points. And by extracting these traces from uncurated action-free videos using a pipeline called TraceExtract and predicting futures via semantic flow matching over B-spline curves, this completely frozen Vero model acts as a universal motion prior.
It's super powerful.
It is. You pair it with just a simple downstream action expert, and it actually matches or beats state-of-the-art vision language action models like Zero-O. And it does this despite seeing absolutely zero action supervision during its pre-training.
I mean, it is a massive shift in how we represent physical intent. To really understand why this specific architecture is necessary, we sort of have to look at the data paradox that's just trapping the entire ML field right now.
Yeah, the data bottleneck.
Right. We have what feels like an infinite amount of physical behavior data on the internet. Like YouTube is overflowing with humans manipulating objects, right?
Yeah.
Cooking, opening doors, whatever.
Sure, millions of hours of it.
But the data you actually need to control a robot, the hardware-specific action-labeled data, is incredibly scarce. It is notoriously expensive and slow to collect teleoperation data for every single new arm or gripper you build.
So the field basically split into two extreme approaches to solve this, and both are kind of hitting severe scaling walls.
Yeah, they really are.
On one end, you have pixel space video models, and these scale beautifully on raw internet video, but they waste immense model capacity reconstructing dense appearances.
Right, the background details.
Exactly. If a model spends all its compute trying to get the lighting on the background wallpaper right, it isn't focusing on the metric geometry and the contact physics of the hand actually picking up the mug.
No, it completely loses the plot.
Eh.
They often fail completely at capturing precise 3D geometry required for actual manipulation.
Yeah, you end up predicting 1,000,000 pixels when only a few hundred actually matter for the physical task.
And then on the complete opposite end of the spectrum, you have the vision language action models, right? The VLAs.
Right, the direct action model.
Exactly. These output the exact motor torques or joint angles.
Yeah.
They solve the physics problem directly, but they suffer from terrible scalability because the labels are tied to the hardware.
Right, they're siloed.
Yeah, if you train a VLA on a robot with a parallel jaw gripper, it has absolutely no idea how to operate a dexterous five-fingered hand. The data is entirely siloed by the embodiment.
Which brings us to Zero's core thesis, which they call the middle ground.
Middle ground, yeah.
It doesn't model pixels and it doesn't model robot joints. It models 3D traces of semantic interaction points. So we're talking about object parts, tool tips, hands, contact regions.
Also about the contact points.
Right. It entirely abstracts away the robot's morphology and focuses purely on what must move in the environment and how it must move.
Think about the underlying physics of a task for a second. If your goal is to, say, open a refrigerator, the 3D trajectory of the handle swinging outward through space is exactly the same whether a human hand, a suction cup, or a two-fingered gripper is applying the force.
The motion is the same.
Exactly. The trace itself is the universal language of the task. So by predicting that trace, Zero completely decouples the understanding of the world from the actual hardware executing the action.
It's like teaching someone to dance by simply drawing the 3D paths their hands and feet need to take through the air.
That is a great way to put it.
Right, because you aren't simulating the lighting in the entire ballroom, nor are you forcing the student to have the exact same muscle structure and limb length as the teacher.
Right. You don't need a perfect physical match.
Exactly. You're just passing the geometry of the intent. Like, move this specific point along this specific curve.
But framing it that way exposes a massive data engineering problem, right?
Oh, for sure.
We know 3D traces are this hyper-efficient, embodiment-agnostic representation. But where do you get the training data? You can't just go and download a massive foundation-scale data set of annotated 3D traces.
Right. You can't just scrape that off the web. So how do they actually build the data engine?
Well, the paper outlines a massive pipeline called TraceExtract, and it's designed to take regular, heterogeneous internet video and pull out high-quality 3D traces.
Okay.
They break it down into 3 crucial stages: deciding what to move, figuring out where to move it, and captioning how it moves. Let's start with the what. How do you decide which points in a video actually matter?
Because previous methods, like TraceGen, they often relied on a blind, fixed grid of points across the image, right?
Yes, exactly. And the problem there is obvious. You waste your point budget on static background elements like the sky or a wall.
Right.
And you often completely miss the tiny task-critical regions, like the very tip of a screwdriver.
Bruh.
TraceExtract fixes this by using DynoV2 patch features to cluster entity-level groups.
Right, because DynoV2 gives you those really rich semantic embeddings. So instead of just dropping points blindly on a grid, the system actually understands the semantic boundaries of the objects in the frame.
Exactly. It knows what it's looking at.
Yeah, it allocates key points proportionally based on those entities, and then it applies a movement filter to just discard the static background points.
Right. It guarantees the model is only tracking the things that are dynamically interacting.
Okay, so once you have the what, you need the where.
Right. The 3D trace construction phase, it requires taking flat 2D video and building a global, local 3D reconstruction. They use a system called VGGT to establish sparse anchor frames across the entire video, which creates this shared global coordinate system.
Okay.
And then they reconstruct dense local chunks of frames between those anchors.
Wait, I have to stop you there because as an ML engineer, this is where my alarm bells are ringing.
Oh, really? Why?
Well, if you are trying to track floating points across a long, shaky, egocentric video like someone wearing a GoPro while making breakfast, it usually results in total chaos.
Oh, absolutely.
Objects get occluded, the camera whips around, lighting shifts. If I just run a standard tracker frame by frame, how does this pipeline not just output pure noise and completely lose the identities of these points?
Well, the compounding error of frame-by-frame tracking is exactly why they don't do it linearly. If you just track frame to frame, a 1 millimeter error in frame 2 becomes a 10 centimeter error by frame 50.
Right, the drift is brutal.
Yes. And that is the genius of using VGGT for those sparse anchor frames. By aligning all the dense local chunks back to those shared global anchors, the alignment errors are bounded per chunk. They do not compound across the whole video.
Oh, okay.
And for the point tracking itself, they propagate world space coordinates using TPP3D, along with those robust Dino clusters we mentioned.
Oh, so if a mug is occluded by a human hand and then reappears, the system uses its last known valid world space position and its semantic identity to reinitialize the track perfectly.
Exactly. It knows it's the same mug.
Okay, bounding the error makes sense, but there's still the issue of camera shake. I mean, if I turn my head, every point in my field of view moves relative to the camera. It looks like the coffee mug is flying across the room.
Right, the egocentric problem.
Yeah. To fix this, the researchers reproject these tracks into a per-chunk reference camera. They effectively just subtract out the egocentric camera movement.
Exactly. The resulting trace isn't polluted by the human's head bobbing around. It just represents the clean, screen-aligned 3D motion of the object itself.
Which leaves us with the final stage of the data engine, the how. We have clean 3D tracks, but we need language to condition the model.
Right, the text prompt.
Yeah, because if you just feed a VLM a massive episode-level video and caption it, "Make breakfast," that is completely useless for learning fine-grained motor skills. A robot needs to know the specific subgoals: reach, grasp, pull, release.
Exactly. So how do you automatically slice a 5-minute video into those micro-actions without paying human annotators?
Right.
They apply a Savitsky-Golay filter to track the acceleration of the 3D traces.
Let's break that down, because a Savitsky-Golay filter is a specific smoothing algorithm, right?
Yes, it is.
Because raw tracking data is inherently jittery. If you just calculate velocity and acceleration from raw frame-to-frame positions, the math gives you a jagged, noisy mess.
Complete noise.
Right, so this filter fits a low-degree polynomial to sliding windows of the data, and it gives you a highly accurate, mathematically smooth curve of the object's acceleration.
Exactly. And once you have that smooth acceleration curve, you basically just look to the valleys. Think about the physical mechanics of picking something up. Your hand accelerates toward a cup, then decelerates as you reach it.
Right.
There's a micropause, a valley in the acceleration right as you make contact before you start lifting it again.
Oh, wow. So the algorithm automatically places chunk boundaries at those low acceleration valleys.
Exactly. Those natural pauses correspond perfectly to the end of one subgoal and the beginning of another.
That's super clever. So once chunked, a vision language model can hierarchically caption these short, distinct motion events. Now you have a massively scaled, highly accurate data set of observations, 3D traces, and specific language instructions.
That's the engine.
All right, so the TraceExtract pipeline has given us our training data. We've stripped away the camera shake, bounded the trapping error, and isolated these clean, floating 3D traces of subgoals.
Right.
But how does a neural network actually digest a floating 3D line? Because standard vision language models, they only know how to look at flat 2D pixels.
Right, so let's look at the actual Auria architecture. The foundation of Zero is a multi-modal backbone, specifically a pre-trained small VLM2 2.2b model.
Okay.
But to predict 3D traces accurately, the model absolutely needs metric depth. It needs to know exactly how far away things are. Metric depth, however, is completely outside the native input space of a VLM trained on regular internet images.
Right. If you just take a pre-trained RGB network and clumsily concatenate a fourth channel for depth, you completely blow up the input dimensions.
Exactly. It breaks the model.
Yeah, you ruin the pre-trained visual statistics of the VLM, causing catastrophic forgetting. You just lose all the common sense reasoning the model learned from billions of images.
So they use this brilliant architectural trick. They take the depth map and route it through a separate trainable patch embedding stem.
Oh, okay.
This dedicated stem learns to project the raw depth data into the exact same latent space as the RGB patches. Only after the depth is mapped into that compatible space do they combine it with the RGB tokens and pass them together into the deeper, shared SIGLIP transformer layers.
Ah, so the network gets to exploit precise geometric cues without destroying its massive generalized scene understanding.
Exactly, and that rich scene understanding is then passed to the core of the model, which is the permutation equivariant trace expert.
Right.
The model treats the key points we found earlier as an exchangeable, unordered set of queries. And here is where the dyno clustering from the data engine really pays off again.
How so?
Well, each query token is enriched with a local dyno feature. So the model isn't just looking at an arbitrary coordinate like point 42. The token inherently knows, I am point 42, and I represent the handle of a ceramic mug.
Oh, I see. So the network perfectly understands the semantics of the specific point it is responsible for tracking.
Exactly. And what those tokens are tasked with predicting is where the math gets incredibly elegant.
Okay.
Because the naive approach would be to have the model regress dense, step-by-step waypoints for the future trajectory. Like predict where the point will be in frame 1, frame 2, frame 3, and so on.
Right. But that's computationally heavy and naturally produces high-frequency jitter.
Exactly.
So instead, it targets 10-degree 3 B-spline control points. For anyone who has used the pen tool in Photoshop or Illustrator, a B-spline works exactly the same way.
That's a perfect analogy.
Right. You don't draw 1,000 tiny jagged dots to make a curve. You drop a few anchor points, control points, and the underlying math automatically bends a perfectly smooth, continuous wire between them.
Right.
By targeting just 10 control points instead of hundreds of dense waypoints, OINI drastically compresses the data. And more importantly, the math of the B-spline guarantees the resulting trajectory is perfectly smooth, which is absolutely critical if you are eventually going to send this curve to a robot's motor controllers.
Yeah, you cannot send jitter to a physical motor. To actually predict the coordinates of those 10 control points, the network operates as a conditional flow model. Flow matching is a generative process.
Okay.
You start from pure random noise,
Yeah.
and the network predicts a velocity field, basically the vector pointing toward the true future positions of the control points. And they use Adelin 0 to inject flow time modulation.
Right. So Adelin 0 basically modulates the layer norms based on the current time step. It tells the network exactly how far along the denoising process it is, which stabilizes the generation. This flow matching approach is so crucial because it allows the model to capture the multimodal uncertainty of the future. Like if a block can be pushed to the left or to the right, the flow model can represent both possibilities.
Right, whereas a standard regression model would just average the two paths and predict the block moves straight down the middle, which is usually physically impossible.
Yeah, exactly.
But generating individual points raises a really critical physical constraint issue. If the model is independently predicting the flow of 20 different points that all happen to be on the same teacup,
Wait, how does the model know it shouldn't rip the solid object in half? Like, what stops it from moving half the points to the left and half to the right?
that is exactly the issue. They enforce the physics using structural constraints during the flow matching objective. First, there is the validity prediction head.
Okay.
This learns to predict when an occlusion means the trace should just terminate, rather than hallucinating a path straight through a solid wall. But the core physical constraint is the semantic rigidity loss.
Ah, the rigidity loss. Think of it as a virtual skeleton. Because the TraceExtract pipeline grouped the points using Dino clusters, the model inherently knows which key points belong to the same physical object.
Exactly.
So the rigidity loss actively penalizes any variance in the pairwise distances between points within the same cluster during the denoising process. If point A and point B are on the same mug, their distance from each other simply cannot change as they move through time.
Right. It acts as a structural skeleton, ensuring the model doesn't accidentally stretch or deform rigid objects while generating the future trace.
So at this point, we have a frozen Nero model that takes in an observation, understands the metric geometry, respects the rigidity of objects, and outputs smooth, highly accurate B-spline traces of the future.
That's the core model.
But, predicting floating neon lines in 3D simulation space is really only half the battle. How do we actually cross the simulation to reality gap and actuate physical robot hardware?
Right, the real world. This is where the sheer leverage of the middle ground representation becomes obvious. Because Doro predicts embodiment-agnostic traces, its weights are completely frozen for downstream tasks.
You don't fine-tune it at all.
Not at all. Instead, you train a tiny, entirely separate action expert.
And this action expert is remarkably lightweight. It takes the intermediate trace denoising features from 0. Specifically, it only requires the features from just one single step of the Euler solver used in the flow matching.
Just one step.
Yeah. And it combines those rich geometric features with the robot's current proprioception, its joint angles, and the language instruction. And from that, the tiny action head learns to output executable motor commands for its specific morphology.
Exactly.
But before we get to the physical robots, we should look at how well Neuro predicts traces compared to other foundation models. On the benchmark trace prediction tasks, it goes up against heavyweights like GPT-5.5, Gemini 3.1 Pro, and specialized models like Track2Act.
And Zero just dominates the 2D and 3D metrics across all time horizons.
Yeah, it crushes them on average displacement error, final displacement error, and fresh hit distance. Plus, because of the B-spline compression and the flow matching efficiency, it runs blisteringly fast.
Yeah, 0.29 seconds per inference.
Right, that is nearly 3 times faster than Track2Act.
The inference speed is great, but the physical robot control results are what truly validate the paper's thesis. They tested this architecture on 8 RoboCasa 365 simulation tasks and 3 real-world manipulation tasks using a UR3 robotic arm.
And the Aura policy doesn't just match the performance of direct action models, it actively exceeds them.
It's incredible.
This is the most staggering claim of the paper, and I want to make sure you really internalize this if you're working on VLAs. The Aura setup achieves 120 to 130% of CO's average success rate and 70 to 115% of P.5 success rate.
It outright beats Zero.
Right. Keep in mind, Visa is a model that was explicitly trained with massive amounts of action supervision. Meanwhile, Zero saw absolutely 0 action labels during its pre-training. How is a model trained entirely on action-free video outperforming a natively trained VLA at its own game?
It all comes down to the quality of the prior. The 3D traces provide such a strong, generalized structural prior of how the physical world operates.
Right.
Because of that, the tiny downstream action head doesn't have to learn the physics of the world from scratch. It doesn't have to spend its limited capacity learning what a mug is, or how gravity affects an object, or how to avoid an obstacle.
Right. ONU has already solved the geometry of the intent. All the tiny action head has to focus on is the specific kinematics of its own robotic arm to follow that geometry.
They prove this empirically, too, with an ablation study on the action head scaling. If you take a 200 million parameter action head and train it on these robot tasks without the Ono trace features, it completely struggles.
Yeah, it gets about a 10% success rate. It just doesn't have the capacity to learn world physics and robot kinematics simultaneously.
Exactly. But if you take that exact same tiny model and simply plug in ONU's frozen trace features, its success rate instantly jumps to over 25%.
Wow, the trace completely carries the cognitive load of understanding the physical world.
The action expert is basically relegated to being just a translation layer. It translates the universal spatial math of the trace into the specific motor torques of the UR3 robot.
Makes total sense.
And because Ono was pre-trained on a massive, diverse video dataset without being restricted to footage that had robotic action labels, its understanding of that spatial math is vastly superior to a VLA trained only on a comparatively small dataset of robot teleoperation.
Which brings up a really provocative thought to leave you with. If 3D B-spline interaction traces are truly this universal embodiment-agnostic language for physical motion, We don't have to limit our training data to YouTube cooking tutorials or human manipulation videos.
No, we don't.
Could we start building massive motion dictionaries from entirely different domains? Imagine running the TraceExtract pipeline on professional sports footage, wildlife documentaries, or even CGI animation.
The potential scale is staggering. I mean, once you decouple the understanding of motion from the specific hardware executing the motion, literally any video showing physical change becomes valid training data for any robot.
Exactly.
We are moving away from learning how to execute specific tasks and moving toward learning the fundamental kinetic structure of physical movement itself.
Yeah. You could create a universal kinetic model where an industrial robotic arm could perfectly execute the complex physical dynamics of a tennis serve, or, the precise sweeping motion of a cat swipe, simply by following the extracted spatial math of those semantic traces.
It is the ultimate form of physical choreography.
You just draw the 3D paths and the robot learns to dance. Thank you for tuning into AI Paper Slop. We will see you next time. Think about what motion you'd want to trace next.